All right, welcome everybody to another Galaxies Science Interest Group seminar. I am absolutely thrilled to announce Clayton Robertson, who is a PhD candidate here with me at the University of Louisville. He's in his final year, and he will be talking about mapping dust attenuation from overlapping galaxy pairs. This is a topic that we've been working on for the last 4 years now, 4.5 years. And he's made great progress. So I'm absolutely thrilled to hear what he's got to say. All right, take it away, Clayton.
Thank you. Yeah, so like you said, we've been working on this for about 4 to 4.5 years now, looking at different kind of unique findings in astronomy, and those are galaxies that partially overlap each other. We call overlapping galaxy pairs, we call them occulting pairs. And what they do is they give unique insight on many things about the galaxies themselves, specifically how they can get backlit and highlights the dust structures. And so that's what the main investigation is using for what we're doing with overlapping galaxy pairs is looking into the dust in the ISM of these galaxies themselves. Oops, that didn't work. That did. Okay. So one thing that we want to, like I said, one thing that we want to look into is dust in the ISM using occulting galaxy pairs. And why should we care about dust in the ISM? Well, for one thing that it's super important for us in our cosmic origins is the fact that dust is full of the heavy elements that we are made of, like iron, silicon, carbon, nitrogen. All of those are ingredients of dust in the ISM, formed in hearts of dying stars and reprocessed back through nebulas, through galaxies and everything all in itself. And dust is everywhere. They give insight on uh, just essentially a lot of the components that we are made of and our solar system is made of, but also from these galaxies that we're looking at far away and everything themselves. And dust will affect all astronomical measurements. They affect things like standard candle measurements in galaxies. They have strong constraints on dust spectral energy distributions. And that basically tells like the galaxy's life story, and the dust life cycle gives us unique insight on cosmic origins of galaxies themselves. And so dust is something that is very uniquely important across all astronomy. And the picture you're looking at right here is the Tarantula Nebula taken by the wonderful James Webb Space Telescope. It's one of the most beautiful pictures I've seen from it. Actually was the wallpaper on my phone for a good while, just because it was so beautiful to look at. And it's mesmerizing. You can see how the dust in the Tarantula Nebula kind of gets in the way of stars in the background. And that's kind of gives a little bit of a peek of what we're doing is looking how dust can get highlighted by this by light that's backlighting it. But before we get to that, let's talk a little bit about how we can measure dust in a way that is a very important. That's very important whenever you're proposing telescopes, you have to take into account dust attenuation and everything like that. Dust attenuation is the combination of reddening and scattering of light due to dust. And so dust reddens it and dust scatters it for the same way that, not necessarily the same way, but scattering is the same way that we have blue. I have blue skies and everything like that. That is Rayleigh scattering. Dust does a different kind of scattering, but it's still the same kind of idea. And the way that it works is that we can measure dust attenuation as a function of wavelength. And depending on the different sight lines you look at, for example, if you're looking through the Milky Way it's different than when you look through the Magellanic Clouds dust. And this is what this plot shows right here, is that I have three different dust attenuation. There are many more. Um, there is a high variety of dust attenuation laws that tell uniquely different things. And one thing that I chose for these three is because these are reddening slope dependent, the RV dependent. They're a dimensionless or parameter RV that predicts the shape, curve, slope, and shape that gives insight on dust grain size. And we can get to that in a little bit later. But for each reddening slope, each RV value gives insight on the sight line you're looking at. So for each of these three different attenuation laws, from Fitzpatrick 2019, Cardelli, Clayton, and Mathis in 1989, and Carl Gordon's 2023 laws. They are RV dependent laws that if you put in different RV values, for example, the Milky Way is 3.1 assumed, SMC is around 2.74, LMC is 3.41, it gives different shapes and it gives different slopes. And and it has different attenuation throughout the entire wavelengths. And so for example, you see this big giant bump here. That is the UV 2175 angstrom bump. And that is something that is very anybody who's studied UV, used UV data is probably aware of that. And that gives and all of these are part of dust attenuation. And so dust has a very large impact on where you go and across all wavelengths where you look at in astronomy. Whether it's the UV in the blue areas where it's very small micron all the way to the visible bands, which is around right here, and all the way out to the infrared, which are obviously the infrared imaging is very hot topic right now because of James Webb, Nancy Grace Roman, and other telescopes, SphereX even, that are just now getting in the process of getting more and more and more data. And so no matter where you look in the kind of wavelengths you look at, dust attenuation is always something that you need to account for because it is accounting for dust. It is it's an optical function. Function might not be the best word there, but it gives a way to kind of predict and account for all how much dust can redden and scatter light wherever you're looking in, where you're looking at, and what wavelengths you're looking at as well. So dust attenuation is what we want to map with occulting galaxy pairs. And so how does occulting galaxy pairs work? Well, we're going to show you the unique one. This is the one where the bulk of my research in the past 3 or 4 years have been on. It's one specific occulting galaxy pair that is beautiful, and its name is VV191. And here's a beautiful picture from James Webb. What you have is a spiral galaxy on the right. That's VV. So bear with me with the names here. But the right galaxy is VV191b. That is the foreground galaxy. That is VV191b. And to the left, it is backlit by an elliptical, smooth background galaxy, VV191a. And what you see is this is what we mean by occulting galaxy pairs and overlapping galaxy pairs. We wanted a partial overlap to where the overlap causes the foreground galaxy's dust structures to be backlit. Because the way dust attenuation works is you have to have something, you have to have a background light source. You have to have a light source to where is dust, what is the light source that dust is dimming? What is the light source that dust is reddening and scattering? What is the light source that the dust is blocking? Right? And for occulting galaxy pairs, that background light source, which is independent of the dust structures of the foreground galaxy, is that background galaxy. So for the things that need to work out for occulting galaxies is that these two galaxies cannot be interacting. They should not be interacting. We don't want them to be interacting. And they want it to be to where one galaxy will backlight the structure. That way it's and the reason we don't want them interacting and really kind of working against each other is because we want the background light source to be independent. We want that background light source to be independent of that foreground galaxy. That way the dust structure, the background galaxy acts like a lamp. It acts like a lamp that just highlights the dust structures in a way that hasn't really ever been before seen because of the unique way it's backlighting those structures. And it gives us the opportunity to map out that dust structure and map out the dust attenuation and calculate dust attenuation along the overlap of these two galaxies. And, so the distance of the foreground galaxy is around 200, so VV191, sorry, let me back up a tiny bit. So VV191, their distance, it's around a redshift of 0.05, which equates to around 230 megaparsec away. This foreground galaxy is an SBC spiral galaxy that is not too dissimilar to the Milky Way, probably a little bit bigger. It is bigger than the Milky Way, but it allows us to look at this face-on spiral galaxy that is not too far away and allows us to map out the dust structures in the spiral arms in this overlap. So you see right here, you see how these dust structures on the outer spiral arms are being highlighted and backlit by this elliptical galaxy in the background. And so this makes this an ideal geometrical candidate for using occulted galaxy pairs. And one thing I also want to highlight is the symmetry on these galaxies. These symmetry, I mean, this galaxy is beautifully symmetrical. It's a spherical background elliptical galaxy and a spiral galaxy that is very, very nicely symmetrical compared to a lot of galaxies that we find. And so how do we calculate attenuation? Well, attenuation is calculated from the overlap in the overlap. So inside the parentheses right here, well, let me back up again. I'm getting ahead of myself. So the background galaxy by itself, we call that B bar. The background galaxy, that is the flux estimation. So F bar and B bar are the estimates of the flux contribution by the foreground and background galaxies, respectively. And so, and inside the parentheses right here, oops, I'm looking at the wrong thing. Inside the parentheses right here is the transmission to where F plus this guy right here. So within the smaller parentheses, that is the optical depth inside the overlap of this galaxy of any whenever you're overlapping occulted galaxy pairs. And then so if you take the optical depth of the overlap, subtract out the background and divide it by the background, that gives you the entire transmission. So inside these big parentheses here, that is the transmission. And to get attenuation is just quite literally multiplying the constant and take the natural log of the transmission and then just multiply by a constant, and that'll give you the attenuation itself. So it's a very simple process that allows us to exploit the background and foreground flux contributions, therefore making it easy to map out the dust attenuation pixel by pixel. So we can do this for pixel by pixel as well. And the image you see on the right here is attenuation mapped in the F606 filter from HST. So I mentioned that we had JWST imaging, but we also have HST imaging. I'm going to go later on, I'll mention exactly how many kind of filters we have from James Webb and HST on this galaxy, but it's a good amount. And one thing I want to highlight here is that this spiral arms, this is the attenuation map. And these spiral arms, this is where the elliptical galaxy should be, is right here. I don't know if you can you see my mouse? Are people able to see my mouse? Okay, I didn't know. Okay, so right in here is where the elliptical galaxy is, and these are the spiral arms that are being backlit by the galaxy themselves. Therefore, this area right here, this overlap region, is where the attenuation measurements are. Where the attenuation measurements are the highest signal noise. And this is why symmetry is very important, because this area in the overlap region is where the attenuation measurements are the highest signal noise and where they're reliable. And so you have to exploit a very symmetrical galaxy that where you can estimate the flux contributions over here by saying the flux contributions over here is similar to the flux contributions on this side. Therefore, the attenuation measurements can be efficient and can be inferred throughout the entire galaxy itself, even though the attenuation measurements actually are for the overlapping region itself. Okay? And so that's what makes VV191 an pristine, opportune candidate for occulting galaxy pairs. So we have what's here is the attenuation measurement. So this is based on the spiral arms themselves causing it. So a lot of it's based on the stellar continuum. There are different kinds of ways to measure attenuation. There are many different ways actually to measure attenuation. And so this is one way itself. They're using a occulting galaxy pair. A couple of years ago, we have a wonderful opportunity to measure attenuation in VV191b in another way, and that's using the Balmer decrement. Oh, that didn't work. Okay, there we go. And so observations from the George and Cynthia Mitchell spectrograph in the McDonald Observatory in the University of Texas got IFU integral field unit observations of this same galaxy pair VV191 that got in this bandwidth. And so for every single pixel in VV191 punched out each pixel or we call it a spatial pixel, so I call it a spaxel, punches out a spectra where it has the Balmer decrement, which is the Balmer decrement is the hydrogen recombination lines of H alpha and H beta. So H beta is right here, so these are emission lines, and then H alpha is over here, and they derive from just hydrogen recombination whenever the n equals it goes from n equals 4 to 2, I believe. Um, Hydrogen recombination lines, you can correct me on that later, but it's a very specific wavelength in which the emission comes from, and it comes from hydrogen recombination. And taking the Balmer decrement, which is basically the emission line from H alpha divided by the emission line from H beta, and you can see, and this is just the zoomed in plot from this side over here, where H alpha and H beta are here, and you can take the emission line fluxes from each of them, and take the decrement, take the ratio of those two, and that'll give you insight on the attenuation itself. It's because the Balmer decrement is very, very sensitive to dust reddening. It is sensitive to temperatures and a little bit dependent on the environment, but is much, much more sensitive to dust reddening. And that's why the Balmer decrement has been widely used for attenuation measurements itself. So these are nebular emission lines, the way we can do it. So that's why I denoted this as AVH2, because these are nebular emission lines, H alpha and H beta, that derive from H2 regions inside the galaxy itself. And so integral field units and the integral field unit data reduction was done by the wonderful Jason Young, which is actually in this talk right here. He was able to be kind enough to take the observations with Dr. Alberta, and we are able to do the data reduction and get the spectra in a wonderful, I mean, it's a wonderful big giant data cube of the entire overlapping galaxy pair, getting the nebular emission lines H alpha and H beta. That way we can map attenuation, not just with occulting galaxy pairs, but also with nebular emission lines. So what we have here is two different ways to measure attenuation. One from nebular emission lines with a Balmer decrement, and the other one was for occulting galaxy pairs. Those are two very independent attenuation measurements. So the logical thing to do from there is to compare them. But before we do that, I want to give you the maps of H alpha and H beta from these guys. And so these maps, so the left is H alpha on a scale of 10 to the negative 17, and the units of ergs per centimeter, let me try this again, ergs per second per centimeter squared per angstrom per arc second squared. And so these are flux contributions, and this is taking the emission lines, taking the area under the emission line and extracting the emission lines to get the H beta maps, and then we can map them and seeing this is where VV191b is. And so VV191b is right here, and then VV191a is down here. Notice that there's no H alpha and H beta contributions from there. Is because VV191b in the elliptical galaxy, that is just absorption. They don't have any emission lines because it is a elliptical galaxy and they only have Balmer absorption lines, not emission lines. And you can see that where H alpha, and actually I'm going to go back 1 second because I want to give insight on a couple things. One, look at the absorption here surrounding H alpha and H beta. What that comes from is the stellar absorption that comes from the stellar photosphere of O and B stars, of these high young stars. They have stellar absorption that surrounds H beta that makes kind of the extraction the extraction of the H beta emission line a little bit more difficult because you can see even a little bit in the blue is the bootstrapping error that's made from the mean and standard deviation of 30 pixel window centered around the highlighted pixel right here. So basically I take an average of 30 pixels around it and seeing what the average is and seeing how much these emission lines kind of differ, and you can see where the emission lines are larger than the bootstrap error. But this absorption that surrounds the H beta emission line is important because those come from stars themselves. They'll come from young stars themselves, and they kind of make the extraction of the emission lines a little bit difficult, which is why you see the signal noise kind of go down, and it's very nice and wonderful with H alpha, and H beta is a little bit more difficult. And I believe that H beta is a little bit has been more difficult to extract the emission line because of that stellar absorption there. So that has been a pain. It's been a pain for a lot of us spectroscopists from what I've seen and talked to, is that it's something you always have to take into account of. And trying to account for it is definitely something that um, has been difficult, and probably in trying to find the best way to trying to counter that and try to account for that has been something that I've been working on, and I'll go into a little bit later, but it's something to keep in mind of whenever taking the Balmer decrement measurements itself. This is another maps that I created, which are contours based on the attenuation maps of the spiral arms themselves of the Balmer decrement, H alpha and H beta, and you can see the uniform distribution and the uniform decrease um, of each Balmer emission line, even the Balmer decrement, um, where throughout this entire galaxy itself. So again, these are two different kind of attenuation measurements, and I know we haven't measured the attenuation yet with the Balmer decrement. That comes in a second, or it comes in a little bit. But these are two independent measurements. One from occulting galaxy pairs. That's what this AV is right here. That's the AV from the occulting galaxy method, and then the contour is from the nebular emission lines taken from a separate instrument, the GCMS, George and Cynthia Mitchell spectrograph, formerly known as Virus P. And we're able to overlay each other and kind of directly compare each other. And you can see the uniform decrease in the H alpha lines and the H beta lines, and then therefore the Balmer decrement. You see towards the center of the galaxy, you have a very high dust reddening and everything, and that's what you expect. You know, H alpha, the Balmer decrement is close to 5. Around the edges of the spiral galaxy, you have it around 3. It is important to note that the ratio of the Balmer decrement, the intrinsic ratio of the Balmer decrement, meaning that if H alpha or H beta is equal to 2.86, that indicates that there is very little to no reddening from dust at all. And so 2.86 is the intrinsic value for the Balmer decrement. That's what you expect to get whenever there's no dust or reddening at all. And you see that and that is something to keep in mind here. So it's around 5 here, so it's high amounts of reddening around a 4, and then out in the outskirts you get around to little to no reddening, which is around 3, which is what you expect. And so this is another plot. This is the radial plots of the Balmer decrement and each HF and H beta emission line. And some things to note here is just look how much of the drop off is for H alpha versus H beta. This partially is because H alpha is a very much stronger emission line from H beta. And so just to plot them on the same plot, it doesn't give a good enough insight on H beta does have a good enough drop off as well. But compared to H alpha, because H alpha is a much stronger emission line, it's tough to tell from that slope. But you can see the downward slope of the H alpha and H beta, which in itself gives it gives insight on a few things. One of them, for example, is the scale length, which is based on the SIG index of this galaxy itself. So the slope of the H alpha and H beta line, mapping it out, gives a unique insight on how much of this galaxy, how much is the distribution of this galaxy radially. And I want to mention one thing is RP is the Petrosian radius of 12 kiloparsec. Again, this is a very large galaxy. The Petrosian radius is a bit more involved than the half-light radius, but because it's independent of distance and insensitive dust reddening between telescope that we're looking at and the galaxy itself. But it's similar in aspects to it's a constant radius that has been that is found by Bill Keel in his 2023 paper on the same galaxy that that gives insight on it's similar in, I would say, use as the half-light radius, but it's a bit more involved to find it. That's all. But this is what was found after extracting the Balmer decrement and getting the Balmer decrement in from each emission line itself as a function of galactocentric radius. Okay, and so we have the Balmer decrement itself, and then now we can calculate AVH2, which is the attenuation from the Balmer emission lines. And it's a very simple process as well. I mentioned before that 2.86 is the intrinsic ratio. H alpha and H beta, these are each emission line taking the decrement. So these values right here are just now just for each value, just plug it in right here. That's the H alpha and H beta. And then yeah, multiply by a constant 2.5 and from the and then these are essentially slopes that are assumed. So KV, KHB, and KHA, there's are constants that are based on pre-assumed attenuation, or not necessarily attenuation laws. In this case, is the Calzetti 2000 law, which is it is an extinction law. But you have to assume that because you basically the way it works is the reddening, you have to assume that there's whatever light you're seeing through whenever you're doing nebular emission lines, is that if you see no reddening and no dust, this is what you should see. And so for KV, it's similar to RV, but it's a little bit different. It's based on Daniela Calzetti's 2000 law, to where the visible band in this sense is because we want to directly relate it to the stellar from the occulting galaxy attenuation, we choose the visible band to be represented with the 0.606 micron, which is the same filter or it's the same wavelength as the H606W wideband filter from HST. That way we can have a direct comparison between AVH2 and the occulting galaxy attenuation itself. Going through the literature, I found that from assuming the attenuation laws to calculate the AVH2, there's not much difference depending on which one you choose because in the visible band, this KV area kind of approaches RV, and because we assume that because VV191 is a very similar galaxy to the Milky Way, we assume the Milky Way sightline. So whenever you have, and you'll see later, I don't want to make assumptions on the kind of silence we want to use because, like I said earlier, they have different different attenuation laws based on the sightline. So I want to use all of the different kind of sightlines, but to be able to first achieve that, I need to we first need to assume an attenuation extinction law right here. I have a way to combat that to where I can directly compare the Balmer decrement and the attenuation of occultic galaxy pairs without having to assume this attenuation law right here. And I'll show you that plot in a second. But I want to make note of it now that to be able to calculate the attenuation here, you have to first see an amount of reddening, but you also have to assume an extinction law, right? And so to be directly compared, so that's one thing that we have to take into account. And so whenever I do take that into account, you get attenuation mapping like this, to where assuming you have to assume values for the K values. So KVHA, so I'm sorry to go back one more second, but assuming the values for here, which is based on the Calzetti 2000 law, you get these attenuation maps. And this is the attenuation maps right here of AVH2. And then for the occulting galaxy one, we call it AV stars. And the reason we call it AV stars is because it's based on a stellar continuum. This is the spiral arms. That is it's based on the stellar continuum of this galaxy itself. So I'll get into a little bit later, but this comes into the fact that this is a direct comparison of two different kinds of attenuations, one from the H2 regions and one from the stellar absorption, which is something that has been studied throughout the entire literature in attenuation, is what is the similarities and differences of attenuation based on nebular emission lines and nebular gas clouds versus the stellar continuum itself. And these are just side-to-side comparisons between the two attenuations from two completely different instruments. The left one is from GCMS virus P, getting Balmer decrement, and then from the Balmer decrement, calculating the attenuation and mapping the attenuation using IFU data. And on the right is using the occulting galaxy method from HST 606 wideband filter. Obviously, the main thing that jumps out at you from this kind of comparison is the differences in resolution, right? So HST pixel size is much, much smaller, and that's on the scale of around 100 parsec, which is around the scales of molecular clouds, versus for virus P, it's about spatial sampling is about 1.5, 1.4 kiloparsec. So 100 parsec versus 1.4 kiloparsec. That's a very large difference between them. And so to be able to compare them, we have to remedy that. And so what I did, it's a very easy, a very simple method of just binning galaxies. So using a little bit of just deduction and a little bit of calculation, I found that one virus P pixel, one GCMS pixel is about 16 by 2/3 by 16 by 2/3 HST. So it's not exactly 16 by 16. It's a little bit bigger, but I'm able to bin superpixels of the James Webb Space Telescope pixels and then able to, and this is what I get right here. This is actually on the same scales. This is smoothed out with interpolation, but it's on the same exact scales as this attenuation map right here. And this is centered on the dust lane that is directly in the overlap region where the highest signal to noise of the occulting galaxy AV is calculated. So I want to zoom in on this dust lane region because that's where the highest signal noise is. And it's a large enough area to we can do direct comparison itself. And then by smoothing, binning the pixels for HST, we're able to match out the resolutions, and then we can allows us for a direct comparison itself. So that's the method of how we want to compare AVH2 versus AV stars. And a little bit out of order. So one thing that I wanted to do first before this direct comparison was to first see how the Balmer decrement measurements pan out for all these different four different kind of silence without any kind of assumptions on RV, right? So again, like I said, you have to assume an extinction on to calculate AVH2 just straight from the Balmer decrement, right? And so to get the best idea of which attenuation law it kind of matches up with, I just want to directly compare the Balmer decrement with um, AV stars itself. And so this is what I did right here. This is one of the big plots of my first paper in 2024. That was I think published around March, April, May, somewhere around those months. But this is a direct comparison of AV stars and the Balmer decrement. And the reason, again, I did the Balmer decrement is because if I just choose the Balmer decrement, I will not make any premeditated assumptions on extinction laws. What I did was I plotted the extinction laws for different RV values to see which one matches up where, right? And so on the left here, you have different attenuation laws from the literature. You have Calzetti's 2000 law. You have the Cardelli, Clayton, and Mathis RVs equal to 3.1 with the Milky Way. You have the SMC and LMC sightlines. You have Naveen Reddy's 2015 paper where she found RV is 2.94. You have in Charlotte and Falls 2000 paper, which is doesn't make it's a little bit of a different equation to find the slope here, but you can plot out the slope, but it's not dependent on RV law, which is why I didn't put an RV value there. But that's from the RV value and different extinction laws and attenuation laws from the literature. On the right side, these are attenuation laws and reddening slope found by Bill Keel's 2023 paper of, or so yeah, 2023 paper. 2022 is when he wrote it. 2023, I think, is when it got published. Of VV191 itself, of these different regions. And so I want to highlight that these are for different zones. I will get back to these zones later on. Because these zones are for each spiral arms. And what I'll say right now is zones 1, 2, and 3 are for spiral arms. And zones 4 and 5 are the spaces in between the spiral arms. Right. And so he found those RV values for VV191 itself for each specific spiral arms. And this is what we find. This is after adjusting for the stellar absorption surrounding and under the H beta line to where we can get measurements that match up correctly with the intrinsic ratio of 2.86. So 2.86 again around right here, which is equivalent to around 0 attenuation. And then you can see where they line up and where they don't. You can see that a lot of values under here, but a lot of values that come from that matches up with the larger slopes from the literature. And you can see that kind of goes along with where the H alpha. So H alpha again gives insight on the signal to noise. That's why I plotted and color coded with H alpha right here. It's because it's synonymous with signal to noise. The higher H alpha emission, the higher the signal to noise there is. All right. So when assuming an attenuation law by picking one of the slopes, and for in this case, we choose that RV is equal to 3.1 by assuming that VV191 and SBC face on spiral galaxy, similar to Milky Way, because it has direct impact on, well, this is the ability to look at a galaxy similar to our Milky Way face on from the outside. We're able to make direct comparisons between AVH2 and AV stars. Okay. And so here's the main results that I find, the main findings shown here. It's from AV and let me start over. So you see these differences in here, but I find it's radially dependent differences. But these difference between AVH2 and AV stars. So the literature predicts that the difference between these two quantities are around 2. And that's based on the two-component dust model, to where one component's from the diffuse ISM, which is right here, which is based on a stellar, which is more dominated by the stellar continuum, and from short-lived stellar birth clouds, which is directly correlated to the star formation rate, high star formation rate, to where there's star forming regions over here. So when you find that when star formation rate increases, there is a greater difference in AV between these two attenuations, and that very much agrees with a lot of the literature. Is the fact that a lot of times on these galaxy-wide measurements, whenever they measure the entire galaxy themselves, they're seeing these differences in attenuations by a factor of 2. I think Daniele Calzetti found it 0.44 is the ratio, which, it's close to 0.5, meaning that the ratio of them is around 2. But what I'm finding is that whenever it's at small scales, the variety becomes a little more radially dependent. And this is what this plot on the right shows, is that whenever you get further and further out towards the Petrosian radius of around 12 kiloparsec, albeit it's at a very low attenuation values, but the attenuation becomes more agreeing around that point. So this gives indication that there is a very larger difference. There's a larger differences and more variety in the differences between attenuation at smaller scales, which is something we want to investigate further at the smallest scales possible. So getting these two different attenuation measurements independently at the smallest scales possible, I think will be very important to understanding these kinds of implications on the two-component dust model, which is a very widely used model to explain dust distributions of galaxies themselves. Okay. So I want to go back to here again because so this sums up mainly my first paper from Robertson plus 2024. And one thing I wanted to follow up with it is I wanted to, with these maps of attenuation, I want to, especially with HST and James Webb, I wanted to find out how we can map out reddening slopes pixel by pixel at the smallest scales possible throughout the entire overlapping region of this galaxy itself. And the reason that's important, again, is we want to do it at the scales of molecular clouds around 100 parsec, and we want to map out these reddening slopes, which, again, I'm going to put out this plot. Again, these reddening slopes are very important on how this shapes of this attenuation curve is used, right? The shape of the attenuation curve is dependent on RV whenever you have widely used attenuation curves that are parameter dependent, which most of them are. And even if they're not technically parameter dependent, these RV values give insight on the different sightlines you're looking at, which are part of the parameters, again, for all different extinction laws. So we want to map them out. And the way we're doing it with the available data is with James Webb and HST. So here are all the observations we have of VV191 overlapping galaxy. It's a good amount. HST3, we have the little bit of the blue HST F336, 0.3 micron. You have 0.6 micron. Both of these are from StarsMog, which is, I believe it's StarsMog. Dr. Verda might correct me on that later. But StarsMog with PI, Dr. Verda, and me. And then from the James Webb, that is from Pearls, which is PI Rohir Weinhorst. So we were able to be a part of the Pearls team to get data from the F090 filter, the 150 filter, and then from the two larger wavelength filters of 3 micron, 4 micron, all of these from James Webb NIRCam. And so these are the available attenuation maps. Each of these, I would say that if we found that the blue HST filter wasn't good, didn't have high enough signal to noise to go through with mapping out attenuation, but we did find some uses with that as well. I'll get to that in a little bit later. But for each of these filters right here, from 0.6 micron on to all the way to 4.4 micron, we have essentially 1, 2, 3, 4, 5 different maps we can create from attenuation of VV191. And then from there, if we have all these attenuation maps, we can map out reddening slopes as well. Because these are in the infrared, we can't necessarily assume we don't have AB. Because we don't have AB right here, this should be our AV. So this is AV over AB minus AB. Sorry. If you want to have lambda here, then this needs to be lambda itself. That was a mistake on my part. But because we don't have AB, we need to have kind of a little bit of a different way to calculate RV. And so we do two different methods right here to where we have A lambda and AV. So for AV, we assume that the 0.6 micron is the visible band, which, usually the visible bands are around 0.55 micron. 0.6 microns, we believe, is close enough, especially since it's a wideband filter, to where the HST map, the HST map of F606 filter will be the AV. That's the normalization factor right here. And then for A lambda, that's the 0.9 micron, 1.5 micron, 3.5, 4.4 micron. And so we have essentially, I'm going to get into a little bit later, we have multiple different maps to calculate RV from different filters based on some of the best telescopes that are available. And so these two laws, Cardelli, Clayton, and Mathis from 1989, where it's based on two coefficients. I didn't put out the coefficients because it's just a lot of math that I didn't have enough space to put in, but these are dependent on their coefficients A and B, and then from there you can determine the reddening slopes from here. And so we can map out the attenuation as long as we have maps of attenuate. We can map out reddening slopes at the smallest scales because we have attenuation maps at the smallest scales themselves. And this is what we did right here. This is what Cardelli, Clayton, and Mathis. So the restrictions on Cardelli, Clayton, and Mathis only allow us to do 0.9 micron and 1.5 micron. That's just based on for allowing us to use that equation. So these are the only two filters that we're able to use it with. But again, using AV attenuation from the 0.6 micron, 0.9 micron is right here. And you can see that 1.5 micron is used with the 0.6 micron as well. Okay. And so again, I want to highlight a few things. Right here is the Petrosian radius. And then the masks, these are just masks that were made out by Bill Kill in 2023 to block out foreground stars and a few other interesting things, but we'll get to that in a little bit. And then each of these 5 zones, these are the 5 zones I mentioned earlier from Bill Keel's paper. And so these are the zones that he made of 3 spiral arms. So here is zone 1, zone 2, and zone 3 spiral arms. And then zones 4 and 5 are on the inner arm regions. And so we're able to map out reddening slopes to directly compare from the dense ISM, which are the spiral arms, and the diffuse ISM, which are the inner arms in between each of these spiral arms. And so we can map out, see where RV is consistent, where it changes, where if there's any kind of gradients or varieties and everything like that, and everywhere in between. And so I need to probably hurry up a little bit more, but these kinds of maps give us insight on where this attenuation. One thing I want to show, and this is from Carl Gordon's 2023 relation. And so, back-to-back relationships between these two. And you see that in the dense spiral arms, you see around a consistent 3.1, but inside the grayness, there's high amounts of variation. So I would say that the dense spiral arm regions show a lot of variation and very high amounts of RV, but whenever on the edge of the spiral arms is where we see a lot of the RVs equal to 3.1, which is the assumed reddening slope of the Milky Way galaxy. One thing I want to note is when we go to higher wavelengths, or higher wavelengths, larger wavelengths, so a 1.5 micron, you see there's a little bit less variation, a lot less detail than 0.9 micron. That's because, from my interpretation, is that it's being the larger the wavelength the observation is, the less sensitive it is to smaller grains. And so the more infrared you go, that is more sensitive to the largest grains in the attenuation slopes. And so whenever the further amount we go, the usefulness of these larger 3.5 micron, 4.4 micron maps is to see where larger grains reside and see how much detail it can pick up on smaller grains or the lack of detail because of the lack of um, information it gets on the smaller grains itself it sees. And so we have two different relations in Carl Gordon's 2023 paper and CC Cardelli, Clayton, and Mathis 1989's paper to have a direct comparison between them. And this is kind of the comparisons we find, is that we find that between Carl Gordon's 2023 and then Cardelli, Clayton, and Mathis RV maps, that around 3.1, uh, which is the assumed RV value for the Milky Way, is when they agree with each other. But you see, as you go in for higher amounts of RV, it uh, there's a little bit of disagreement. Same thing goes with the lower amounts. And again, this relationship between these two is just mathematics, right? Because both of those are mathematical relationships from each other. But it's interesting to see where they agree and disagree, and seeing what the kind of assumptions they provide based on where they agree and where they don't. And you see that for when you go to a larger wavelength, 1.5 micron, that you get a little bit of a larger, they agree at a larger value for RV, not necessarily 3.1. Yeah. Because we're running a little bit on time, we're running short on time, I'm going to have to skip through a few different things. Mainly that I created more maps based on color excess ratios, which is a similar, it's basically the cousin of the reddening slope, but but in a sense, these create different kind of maps based on extinction slope. So this is the selective normalized attenuation. And same thing for these math, like and again, the way I calculate that is by assuming RV is equal to 3.1, we can calculate the color excess here. And then from there, we can get the normalized extinction or color excess ratios. And this is what we get. And there are some uh, very important results based on extinction laws of the normalized attenuations based in the literature itself. But again, I'm a little bit short on time, so I have to go very quickly now with this. But one thing I want to show you guys is that I was able to make a mean extinction curve based on the maps themselves, just based on the maps of the selective extinction curve. So that was one important thing coming from the normalized extinction slope, is to see within the spiral arms and the inner arm regions, what do the slopes match up to the literature? And you see from the dense and so again, the arm region zones 1, 2, and 3 are the spiral arms, and then zones 4 and 5 are the diffuse ISM, which is in between the inner arm regions. You see the large difference between the dense and the diffuse, and the fact that the dense regions more or less agree with the literature from Rieke Lebowski, Fitzpatrick, and Massa in 2007, and Martin Witt in 1990. There's a lot more agreement in the slope and the shapes there versus what we're finding in the diffuse ISM. Yeah. Similarly for the attenuation laws themselves here, and I put down a few different maps themselves here that show out kind of agreements and disagreements here about where these attenuation laws agree with the literature and where they don't. And so in the red here for Hensley and Drain 2023 and Bruce Strains 2003, those are dust green models themselves. And so it gives insight. So these kind of plots here give insight on not only how the attenuation slopes agree with the literature in the near infrared, but also it gives insight on the dust grain sizes that throughout. And you see that there's more agreement in the dense arm regions versus the inner arm regions themselves. Okay. One last thing I want to highlight is there's a region in the bottom left of spiral arms, and this is the bottom region of zone 2. And I want to, here, I'll show this area right here. This area right here, you see it's all been blocked out because that's not necessarily a foreground star. We believe it's an area for a PDR. And the reason we think it's a PDR is because using the HST F336 filter, this is what that overlay, this is what that contours. That is the HST F3, so 0.3 micron filter. You see that there's a little bit of blue in that area that's carving out dust. And we believe that's because it's from young O and F stars that are carving out space, creating like a crater, and seeing how much of that is kind of pushing out the front. And from right here, this is a map of the F356 and 444 filter, which gives indication based on Sharon Mead's 2012 paper that there's a correlation between taking the color of 3.5 micron and 4.4 micron and the 3.1 micron pH dust emission feature. So that red that you see in here gives indication of a 3.1 micron PAH feature, which also gives indication that there's a PDR here carving out dust in space. I kind of made a diagram that kind of summarizes that here to where we're using multiple different filters to try to analyze what this PDR is happening and what it's doing in there. So in the middle there, the HST 0.3 micron filter finds that while there's no dust in there, there are some high blue, high 0.3 micron intensity in there, indicating that there's possibility of hot O and F stars residing in the middle. The HST 3 micron and 4 micron colors in there indicate that maybe there's a 3.1 micron pH feature surrounding those O and F stars. And then what those stars and those pHs are doing is carving out dust in there to where there's no RV and AV in this area, but it creates a crater of high attenuation and rending slopes um, surrounding it, in pockets of high opacity with high attenuation values of zero point 0.6 or higher. And that's what these gray spots are. Okay. One thing we want to do next with these is we want to see with HST and James Webb narrowbands, we want to analyze this PDR region to see how much kind of hydrogen ionization is coming from there so we can get the narrowbands to kind of isolate the Balmer decrement itself. And then we can get pH imaging of aromatic infrared bands using MIRI, because if we see the pH features in 3.1 micron, that gives indication that it will be even larger features in the 7.7 micron, the 11.2 micron PAH feature, polycyclic aromatic hydrocarbon features. All right. I'll give a short conclusion here. I'm going to leave this up here, but essentially this is all the points that I made earlier in this talk is essentially using the occulting galaxy methods to derive attenuation, using occulting galaxy pairs, and having attenuation from the Balmer decrement to compare it to, along with mapping out rending slopes pixel by pixel using multiple different filters of the occulting galaxy attenuations to get some of the RV maps at the smallest scales of the highest resolution. Okay. And so that's about all I have for today. Hopefully, I'll leave enough a little bit of time for questions. And thank you.
Hi. Very nice. Thank you, Clayton. Are there questions from the audience? Because I'm not going to be that person to ask questions first.
Hey, can I ask a question?
Yes, absolutely.
Yes.
So one neat thing that you did was compare the reddening from the Balmer decrement to the stellar continuum.
Mhm.
I'm actually curious about getting the reddening from the stellar continuum. Could you speak a little bit about that?
Yeah, so the reddening from the stellar continuum is actually based on, try to go back. Oops. Looks like it's not letting me go back. One thing that the reddening of the stellar continuum is based on the occulting galaxy methods. And the reason that we let's see what I have. So the reddening of the stellar continuum comes from the spiral arms themselves. And so those are based on SED fits. Those are based on a unique method of getting the reddening of the stellar continuum based on the overlap of these galaxies themselves. And so these spiral arms is the features here. That's a lot of it's based on that stellar continuum. And so the reddening in the stellar continuum is finding out how much of those spiral arms reddening the backlight itself. And so that stellar continuum is reddening out the background light source itself. I'm not the way I understand it is that the spiral arms themselves are the stellar continuum that is reddening out the backlight source. And so that gives a direct kind of attenuation measurement of those stars itself. That makes sense a little bit. I think kind of
Yeah, thanks. Can I ask one more question too?
Yes.
So based on the small scale variations you're seeing, do you think that we functionally have now, based on these results, a grain size map? Like, do you think we have enough information to kind of back out maybe a typical grain size or some map of information about grain characteristics?
I believe so, based on the fact that are you talking about for the attenuation slopes themselves that are like the mean attenuation slopes that I plotted?
Yeah.
So I believe so, just because we have a lot of literature to compare it to. I would say that the slopes themselves, and one thing I want to highlight with these three, at least for these three in the dense spiral arms, is that the shape of the slopes themselves show that because they're not necessarily like they're kind of uniform in the fact that the zone one seems like it's the highest slope versus zone two and zone three are lower slopes, that it gives us insight on the dust grain distribution just from that itself. Um, it would be very much nicer, I would think, to get more filters as well, but
Of course.
getting from these four filters themselves, I think it does give a good insight on the grain size distribution just because we have a lot of models to compare it to itself. And so just from this, it can see a few different slopes that show that, yeah, we can get some good distribution size and more data, obviously, is something you always want, but I do think that we can make some solid assumptions based on the slopes and shapes of these curves.
Well, cool work.
Thank you.
Nice talk.
Any other questions? This is a discussion that me and Clayton have been having. Like, is this geometry or is it dust grains? And that's we're getting with this kind of resolution. You're getting to the point that geometry is harder and harder to invoke. I mean, it's turtles all the way down, but you still are now talking about molecular cloud sizes, so sort of homogeneous. Any other questions? We're coming up on the hour. We have a minute left. Any questions? Aaron is laughing, but he's a theorist. He doesn't have to deal with dust if he doesn't want to. He can
Oh, we deal with dust. We just don't. We are not very good at dealing with dust. Put it that way. So we need all of these constraints. Please keep doing this.
Yeah.
So I guess a reminder to everyone or people watching this on YouTube toward the end. Our next seminar is in 2 weeks. Will be given by Ryan Sanders. So join us.
See you in 2 weeks.
Thank you for having me. Thank you for everything.
Thank you all for joining us. I'll see you on
if you
2
have
weeks
any questions, or
Reach
anything
out
like
to
that,
Clayton.
we'll be looking for postdoc jobs very soon as well.
Gotta get that in there.
Yeah, I gotta get that in.
All
righty. Thank you for having me, and I'll go ahead and stop sharing.
Take care. Bye-bye.
All right. Thank you.